Hi, my name is Pramod from the CoinOp Collection Group, and I'm going to show you in this video some of the strategies and tools that I use to resolve timing issues in a core, where they come from, why they come up, and what you can possibly do about them. Everyone at one point or another who has written a core before has had to deal with timing issues. Now, timing issues come up in Quartus by means of the timing analyzer, which is called TimeQuest. Okay, and when you fail timing, this node appears in red. This timing analyzer node appears in red, and you have a bunch of items that are in red over here, right? And at the bottom of the screen, you'll notice that you get some timings, right? So you get your worst case setup, you get your timing requirements not met error message. You get your worst case setup slack, which would be negative. Hold is fine, it's above 0. And recovery is also in the negatives, which is bad. Okay. Now all these timings are of the slowest model, right? So there's different conditions under which an FPGA can operate, right? So if you're, for example, if you're building something for NASA and you're sending a device that has an FPGA up into outer space somewhere on Mars, right? That is a different thermal condition, an environmental condition, than somewhere here on Earth in the summertime, in the wintertime, in the spring, and so on. So the timing of an FPGA or the performance of an FPGA chip depends on one thing. It depends on the thermal cooling that it has available to it, right? Whether there's a fan attached, or where it's enclosed, or other sorts of environmental factors, right? And so Quartus, in Quartus, you get these tools to use to assess what your FPGA program would look like under these conditions, to assess what it would be like under these types of conditions. Now, the default ones are like the best possible one, like you have like really awesome cooling in there. I mean, not like too cold, but not too hot, like kind of in the middle. There is a really slow one, which is like you're super hot, like you're like burning, you're on fire on the sun or something, right? Like, so there's different sorts of things, and these timing requirements are always done under the worst possible conditions, right? To tell you, the programmer or developer of HDL, where your design might fail under certain duress, right? Okay, so typically, what I do is I go into Quartus, right? I do a build, so I've done a build of the YUnit core here, as you can see, and my worst case setup slack is -3.6. Recovery, I don't really worry too much about. I usually worry about achieving the setup, and the rest of it will take care of itself. And generally, the number that I look for here is something under 1 clock period. If it's like, okay, so for example, if I usually I operate at a 96 megahertz clock. If this is under, yeah, if this is around this, or maybe like a little bit lower than this, I think I would be fine, and I would normally ignore it. If it's something like way above this, like if it's like in the 6s or the 7s, and my main system clock is like 96, usually I would have to work on it and figure out what's going on, and how to fix that. And so one of the first things I do is, after a build is done, I will go into the summary, right? I'll go into the timing analyzer, and I'll take a look at the timing closure recommendations. So these are like the top failing paths, right? As you can see, right? And we'll talk about what this means in a minute. But these are the top 5 failing paths by slack, right? So you see this slack, this worst case setup slack right here at the bottom. They basically took the top 5 ordered descending, and they just popped them in this report. Now, what I'm saying to you is, don't look at this report, okay? You definitely do not want to be, focused on this report, because this report doesn't really tell you a lot of information. And secondly, it's only the top 5. There could be something underlying that you'll miss if you look at some other report that's in Quartus, that not it won't necessarily contradict this one, but it will actually give you more information on solving the root cause, because you can have a cascading effect, right? You can have one thing that's failing that kind of cascades into a bunch of different things, right? And you want to solve that root cause, which will resolve everything, right? Let's say if it's part of a larger system. Okay. Now, so what I usually do is I go into here, and you can certainly go into here. This doesn't really tell you very much, and this also doesn't really tell you very much, so I would skip that. And don't worry about unconstrained paths. Let's go to TimeQuest. So I'll click that, and then I will move this window over here so you can see it a little better. So at first, it's going to actually prompt for generating the base timing net list. So you just do that. And so you can see here on the operating conditions on the top left-hand side, these are the operating conditions that I was talking about. Like really testing your HDL model against different operating conditions and simulating what the FPGA would perform under, right? Depending on the environmental conditions that it would be under, right? Depending on where you're sending this device that you have the FPGA chip in, right? So the first thing I do is I go here to the reports at the bottom, and I do report top failing paths. That's what I usually do is first. So I do that, and I get the top 200. Okay, now this gives you the top 200 by default, but if you click here and you press up, what you can see is this number here. You can actually put that as like 1,000 or 10,000 or whatever have you, because as you can see, the top 200 may not cover everything. It only goes like this particular list goes only up to a -3. So you want to get down to 0 potentially. But resolving these would probably go a long way. Since you see, like if you sort them by from node and to node, right? You'll see that it's all kind of the same thing duplicated like a bunch of times, right? It's all the same regs or nodes that are in your core that are duplicated multiple times over. And just before we get into this and do kind of a deep dive into how I would research these types of problems and how I would resolve them, I just want to say that generally out there, if you search on YouTube, or if you search on if you search on Google, there is very little simple subject matter covering this topic. Like most of the videos that I found in the past to help me with this problem were very technical, right? And they kind of missed the point. Like and a lot of the videos like on this topic seem to assume you know what you're doing on top of it, right? Which I mean, not everybody who's starting out obviously knows what they're doing, and has a hardware background, right? So that's why I wanted to create this video to show you how in layman's terms I would go about this topic, and what does it actually mean to fail timing, right? So let's talk about that first. Let's talk about what this actually shows you, what this actually means. Okay, so by default, when you build a core, everything that evaluates timing assumes that data travels from point A to point B in one clock cycle. Okay, and what does that mean? Okay, so let's say your system clock is 96, right? And let's say you set some data somewhere, right? Let's say you set the value of a register somewhere, right? The thing that is using that register that you set should have the data available to it in one clock cycle or less to be considered passing. Okay, so by the time, so this is something that you normally don't think about when you're doing like a software program. Like when you do a software program like in Python or C or something like that, you assign a value to a variable, right? It should be available to you and be set on the next line. It should, right? The reality is in the FPGA world, that's not always true, right? Because in an FPGA, you have different sorts of types of registers or cells, right, that are available to you to write to, right? There's different sorts of things and logical elements that you can use in order to distribute your data, propagate your data, set it, push it somewhere else. Like there's different sorts of types of cells that you have. They call them cells basically, and you'll see that in a minute when I show you the chart. But basically, there's different types of things that are in an FPGA. It's not all just one type of thing, and there's all it's just logical elements and block RAM, and it's all the same. It's all different types. No, it is all different types. Even for block RAM, there's like M9K, there's M10K, there's all these, there's smaller ones, there's labs, like there's different types of units that you can use to put data into and get data out of. Some are faster than others, actually. So the type of cell that it uses happens in the synthesis phase. Okay, so when a core when you're building a core, right, and you're undergoing the synthesis phase. So like the synthesis phase, I'm going to show you here. As you see here, this says compile, design, analysis, and synthesis, right? This is where it actually maps what you have in that you wrote in HDL to the actual elements that it will use, and the fitter step actually arranges them so that they're efficiently using the space on your FPGA device. Okay, so going back to this now, so you have all these different types of cells, and you have all these different types of units that you can use in an FPGA core, I'm sorry, an FPGA chip, right? The chip that you're using, and the synthesis process is responsible for mapping what you've written to what is in the actual hardware. And how does it know that? How does it know how to do that, right? It knows how to do that because internally in Quartus, you have to set the chip that you're using. And this tool is obviously built by Intel, right? This is a purpose-built chip for their FPGA chips, right? This is not compatible with Xilinx, for example. This is not compatible with something else, right? This is only compatible with Intel's Cyclone chips, and I think there's a couple of other models that it's compatible with, but basically it's Intel, right? And so Intel has put in support for the device by they have like a whole engine that takes your code and intelligently tries to map it to things that are on the chip and to use the space more efficiently. Now, I use that term very loosely because when you talk about building a core and you talk about synthesis, there are different ways in which the engine can do that, right? So let's say you're overly concerned about space. Like, so I'll show you right now, right? So let's say you go into where is that now? If you go into tools, options, oh, I'm sorry, project, sorry, assignments, pin planner, settings, right here. Okay, so if you go into compiler settings, right, and you see the optimization mode, you see like there's all these different types of ways that the engine can take your code and map them efficiently to cells on your FPGA device, right? So let's say you were very concerned about your power consumption, right? This mode would basically optimize your power consumption to be lower while also trading off to the runtime and performance, right? Because if you're not giving your FPGA chip a lot of power, let's say you're in a situation where you want to optimize battery, right? And you have a battery on your device, you're actually going to want to use less of it, right? And so the less battery you use, the less power you use, the slower your FPGA chip would operate, right? As an example. And then on the opposite spectrum, if you want to do something that's related to performance, which is what I usually use, I usually try to do this because I'm concerned about how fast something is running. Power is not an object for me. Like power is not a big concern because we have we plug into an outlet, right? In most of our scenarios, or if, I mean if it's on the analog pocket. I mean we usually do performance because usually the power stuff takes care of itself. I don't really see a big difference between these two. We're not what I'm saying is we're not in a very extremely low power situation like you have two AA batteries or something holding this thing up and it has to last for like a week, or something crazy like that. And then lastly we have area. So area is an interesting one. Basically, what area does is it minimizes the space under which a design takes on the chip, right? So you might want to do this mode if your core is really big, let's say for example, and you have trouble fitting it all. This might help you get it basically under the bar. I mean, it doesn't work miracles, but it basically might help you get it under the bar to clear it. Okay, so that's kind of a little bit of the background of this stuff, right? Is basically when these types of timing issues come up, it means that the cells that the synthesis process has mapped your code to, and the registers that you're using, and all the data elements that you're using, and the logical elements that you're using, there is a problem from point A to point B in one clock cycle. There is a problem going from point A to point B in one clock cycle. So the thing that launches this, like the thing that starts this process to the thing that ends this process, there is a risk that that data will not be available to this end node in one clock cycle. That's basically what it means. That's basically what what this is telling you. Okay. Now, there are things you can do to work around this process, right? So everything doesn't necessarily have to be in one clock cycle. There is a thing called an SDC file, so a system design constraint file. Okay, and I'll show you what that looks like right now. So let me just go here to files, for example. I'm using this because, oh, well, actually, I could use Visual Studio, but I also use Visual Studio. Let me just see here. So I'll just open up the SDC right here. So the SDC here is a pretty basic SDC. As you can see, I've not ignored anything here. I've not added any entries. These are the default entries usually that I would put for JT Frame and Mister. These are the default entries that I've put together. But you see here, there's a directive called set multi-cycle path, right? And so you can see that there are from this clock to this clock, right? We're telling TimeQuest that could take up to two cycles, right? So it's not going to take one; it's going to take two. Okay, and what that tells TimeQuest is, okay, evaluate these conditions under 2 clock cycles, not one. Okay, and effectively that may, I mean, if that is your problem, 9 times out of 10 we don't need to go past 2. But if there is a pathway that that you have, that will just eliminate it from the report and it'll just ignore it. Now, even if you ignore something, it doesn't it doesn't actually make the problem go away. What happens is it just masks the problem and it could potentially make it worse. So I try not to do this. I try not to add. I do if it comes time to things, I may add entries into this, from time to time, but it's very rare. And I usually try to do it as a stopgap, so that I can investigate another root problem, right? So if you add entries into this SDC, right, what you can do is you can actually just run timing analysis only again, and it'll reevaluate it under the new SDC. So you don't have to rebuild the whole thing over again. And so that's what I usually like to do for some problems. not all problems. I usually try to add exceptions in here just to kind of get down to the root of the problem, because like I said, in this list over here, there can be thousands of entries, right? I mean, if you really run the report, there could be thousands of entries, and they're all really the same, right? They're all really the same entry here, multiple times. I want to get down to the root of the problem, so I might, ignore this or ignore these things, or just try to get it down to like what is the root cause of the problem. And so I might enter in items in there. You can also right click, by the way, and you can set multi-cycle between these nodes. You can do that, and it does it right here, and you can really evaluate it. But I usually don't do that. Usually I try to go one by one. Well, not one by one, but I try to go from the top, the worst possible things, to the bottom. If I sort it by slack, usually I'll try to figure out if there's any sort of thing that that sticks out to me, that I can investigate, and just go from there. So okay, so what do I do when I'm investigating a particular pathway, right? So this is a pathway, right? So there is a variable called cur_mc_inst, right? And there is a connection between that register and this. And that supposedly takes longer than one clock cycle, right? Don't worry about the launch or the latch clock or the relationship or any of these stuff on the right hand side. Don't worry about that. Just worry about these two. Okay, so what you do is you right click and you report timing. Okay, just click report timing. You don't need to, and always choose setup. Like I said, I'm only concerned with the setup usually, because the rest of it resolves on its own. Once you get the design corrected, the rest of it just kind of falls into place. But you want to see what the problem is. So you do report timing, and you get these fancy charts. Now, as you can see, right? So this is where the data is used, right here. And you can see that you see this data arrival. You see, it's supposed to be here. It's supposed to be here, is where the data is supposed to be available. You see, it's extending on, and it's available right here. So there is a delay of negative 3.607 nanoseconds, right? That's the problem. That's really the problem, of what the situation is. This is a violation, and it's available 3.6 nanoseconds too slow than when it should be. Okay, that's the crux of the problem. Okay, now if you go to data path here on this side, you'll notice that it actually shows you what is the problem, or what is the area that it's talking about. So you want to start with the one that mentions your node, which is right here. Don't worry about any of this before stuff. I mean, that could be a factor, but don't worry about that right now. So you start from here and you go down, right? So this is the data path, right? It's going through this cell, right? And it's going through, and then it's going to outputs. There is a combinatorial statement there. There's a bunch of them actually, right? And then finally it reaches its destination, right? So when you see a lot of these types of combouts and all that stuff, that probably means that you have too much combinational logic in between this from and this to. Okay, it means you're using too much. You're not using the assignments. It could be that you're not using the assignments properly, because like there's two ways to assign something, right? You can do an asynchronous, or you can do a synchronous assign, right, to something, and or you have something that is stretching way beyond, like you're going from one module, you're going several levels deep into another thing, and it's the same one all throughout. You're just assigning it with a wire or something, and you're connecting it all the way across, and you're using it in 50 different places. Like that increases your combinational logic that you have in the middle, and it's going to cause delays, right? Because if you think about it this way, like if you have one tiny cell and you need to use that cell among like 50 different things. Let's say you have one cell that stores a value, and that value is supposed to be used in 50 different places, and it's all simultaneous, right? That's going to cause delays because all those other areas that have to read this value from that cell are going to start hitting it, right? And that will cause delays, right? As an example, okay? What I would normally look for in the code is I would start from here, right? So it tells you the hierarchy path. So it's in EMU, it's in game, right? Which is my top level module. In JTFrame, you have to supply a game top level module. And it's in the CPU. Okay, so it's in my CPU. And there's a thing called cur MC inst, right? And don't worry about the bit value. I usually it's like the whole thing that I'm concerned with. I'm not usually concerned with particular bits in a larger net, right? I'm usually concerned about the whole thing. So there's probably an issue, and I know about this issue already, so I'm going to tell you. Basically, this issue, yes, it's probably right. There's too much combinational logic between this and other areas. Never mind this 2, right? This 2 could be anything. There's a bunch of this 2 that it goes to, but there's basically too much combinational logic between point A and point B. Okay, and you can actually get something similar to that by running a recommendations report. So you can search for, let me see here. Whoops. What happened here? Where's my other thing? All right, let me just run this again. So report timing closure recommendations. If you right click that, click OK. Okay, and you see, indeed, interpath competition. See, that is the scenario that I described where you have some value in one area, but you're using that same value in 50 different places without latching it to another thing, right? Like another reg somewhere, right? And also there's a long combinational path, right? Which it stretches all the way throughout several levels deep into other modules or other things, and it's used in many different places, right? As an example. So what are some of the ways to resolve this now, right? And what is this report actually telling you? So this is a report that's supposed to tell you how to resolve the issue. Unfortunately, it's not written very well. and if you read this, nobody knows what the hell anybody's talking about, right? Reduce levels of combinational logic. How do we do that, right? How are we supposed to do that? One strategy, and actually the chief strategy that I use, is to latch that value into another register when a process starts. So for instance, if I have a value that is supposed to be used for a process, a long-running state machine, let's say, for example. So let's say you have one value that's produced in one module, and it's supposed to be propagated to a state machine, which uses that value a whole bunch of times in its logic. What I would do is, in the first step of that state machine, I would latch that value into another register. And what that does is it takes the pressure off, at least from that state machine's perspective, it takes that pressure off of that cell, right? And that problem will go away, right? Because if you have a long combinational path, what you can do is you can take that value, you can latch it into another register, stop using the initial value, until you launch the process again, and then continue using that temporary latched value all throughout your code. And that is probably the strategy that will resolve. Will probably resolve it in a lot of the cases, but that's not always easy to do, right? Like you can't always, because that basically means that you're delaying your logic by one clock cycle, right? So instead of being available immediately, it will be available one clock cycle later, right? Because you have to basically latch that into another register, not combinationally assign it to another wire. That will not work. You have to assign it to a register um, in an asynchronous block, right? You have to use a non-blocking assignment, right, to do that, right? And then it will latch that in and it'll be available to in the next clock cycle, right? And so you're introducing delay basically to solve this issue. And so and not I mean so it's not that's what I'm saying. So it's not always easy to do in that case. In some cases, what you can do is also reduce the hierarchy among the logic, right? So let's say you have this sprawling thing that goes through all these different modules, and ends somewhere else, right? What you can do is you can cut that logic down. You can streamline it. You can reduce the nodes in between. That usually does not resolve things for me a lot of the time. I generally do not do that strategy. Well, I do it sometimes, but I don't really do it all the time because it doesn't help very much. Because even if you cut this down by like 5 or 10, it's still bad. Like let's say so somewhere along the line you'll need to add delay in order to resolve this problem, right? That's the fact. So let me go back here and report timing. So going back to here, right? So this is generally, I mean, what you're trying to resolve. You're trying to delay this so that this data arrival goes here, right? And in order to do that, you'll have to delay this by 1 clock cycle, right? As an example, right? You'll have to do that in order to do that. So another solution to this problem is potentially to rewrite your code so that the synthesizer maps it to a faster cell. Yeah, good luck doing that. That's not that. I mean, that is an option for FPGAs that are more higher end, that have a lot more of those types of things, those types of higher level cells that operate very fast. But it's not an option that's very practical a lot of the time. But that is an option. That is an option. If you're working with higher end FPGAs, they will have more options for you, like between faster and slower types of cells, more efficient types of cells, or cells that operate very quickly, right? And so you can rewrite your HDL or use other mapping utilities like directives to make sure that the synthesis process actually maps it to that faster but more limited type of cell. And this way you'll be able to accommodate the bandwidth so the data arrives on time to the different places that it needs. So that in a nutshell is those are some of the strategies that I would use. So I would always use the top filling paths report. I sometimes use the recommendations. I always use this report timing report, where I can see the chart, the waveform, and how much it's delayed, and what is going on. And this is very critical. I always use this data path when I'm researching these types of issues. So that is that's in a nutshell how I would go through this. And I would go into the code. I would see like, oh, okay, yeah, there's a problem here. I'll try to latch it to something and see if that corrects the problem. I'll run this whole thing again. I'll see if it corrects the problem. If I'm heading in the right direction, then that is a good sign, in terms of resolving the issues. And then it is a matter of seeing if I have to change any other logic to accommodate that change, right? Because once you start delaying things by 1 clock cycle, a whole bunch of other stuff gets thrown off, potentially, right? And so you might have to go into the code and do that. However, on the bright side, what it means is, you see these operating conditions. It means that you would have accommodated the worst possible conditions under which your FPGA design would be run under, right? So that is a positive, right? You can accommodate any condition. And if you talk about Mr., I mean, there's a whole wild number of conditions that you can have, right? First of all, there's different cases out there, right? There's different cases that introduce heat. There's cases that dissipate heat more efficiently. There's like somebody could be running this in, you know, Florida somewhere where it's very hot, and things are always heating up. Somebody could be running this in Antarctica somewhere. I mean, who knows, right? Who knows where they're going to run this? So you want to be able to accommodate as much conditions as possible, with the setup. You don't want to introduce problems, is what I'm saying. Yeah. So all that is about resolving timing issues and how I do it, and how I mean, I don't know if everybody does it this way, but this is the way that I usually do it. And this is the way I usually research these types of problems. Is I always go through this same workflow.